السلام عليكم ورحمة الله وبركاته. هذه المحاضرة الثانية من هذا الفصل الدراسي الثاني، فراح أعتبرها lecture 2، ما راح أعتبرها أنه هذه part 3 from lecture 1، راح نعتبرها lecture 2 حتى نكمل، حتى يكون العدد عندنا صحيح. وأيضا غيرت الترتيب بالمحاضرة مالت الانترودكشن، إذا ترجعون عليها مرة ثانية راح تلقون أنه هذه هي lecture 2. قبل لا أبدأ بالمحاضرة بس بما أنه إحنا ذكرنا الانترودكشن، فأحب أن أحكي لكم شيء عن الانترودكشن. الانترودكشن مطلوبة منكم أن تقروها حتى تفهمون الموضوع، يعني ما راح أجيب عليها أسئلة بالامتحان، فقط حتى تفهمون الموضوع. إذا تشوفون نفسكم أنتم مفهمين الموضوع بدون ما تقرون الانترودكشن أوكي، بس إذا شفتوا عندكم أي مشكلة بالفهم لازم ترجعون للانترودكشن، ماشي؟ فخلينا نبلش بموضوعنا اليوم اللي هو anti-cancer agents, alkylating and methylating agents. Okay, we discussed the agents that target DNA. Today also we are discussing agents that target DNA, but today we are talking about agents that alkylate or methylate DNA. So what are those agents? Those chemical compounds that contain highly electrophilic groups. Okay, that's why they are highly reactive compounds. They form covalent bonds to nucleophilic groups in DNA. Unlike intercalating agents, those form van der Waals interactions or ionic or hydrogen bonds, but these agents form covalent bonds. So once they alkylate DNA, that's it. They prevent replication and transcription because when they alkylate DNA, like at nitrogen 7 of guanine, okay, they will prevent replication and transcription because they will prevent the enzymes from working on DNA, the replication enzymes or the transcription enzymes, okay? The problem, these agents are highly electrophilic and highly reactive, and that's why they have toxic side effects, because they also alkylate protein, because as we know proteins also have nucleophilic groups. Okay? Not only DNA, proteins also have nucleophilic groups. These agents used as anti-cancer drugs or anti-cancer medications, that's why we are discussing them in this course. As we said, they form covalent bonds to DNA, so they can cause interstrand or intrastrand cross-linking. When that happens, if two electrophilic groups are present. So if the agent has two electrophilic groups, that agent can cause either interstrand or intrastrand cross-linking. And as we say, they prevent replication and transcription, but also the activation of nucleic acid bases can result in miscoding. And when that happens with monoalkylation. Okay? So if the agent only alkylates one position, that might cause miscoding. All right. We said they can cause cross-linking. So what do we mean by that? And we said it can cause intrastrand and interstrand. And so what do we mean by inter or intrastrand cross-linking? In the case of intrastrand cross-linking, the two nucleophilic groups are on the same strand. Okay? As you know, DNA is a double strand. So in the case of intra-strand cross-linking, the agent will come. Yeah, these are the electrophilic groups, and those are the nucleophilic groups of the DNA, right? So then the agent will alkylate those, and that will form cross-linking. We call that intra-strand cross-linking because it's on the same strand. I think it's obvious what the interstrand would be. Interstrand would be when the two nucleophilic groups on each on one strand of DNA. So they are not on the same strand, but each one is on a different strand of the same DNA. So when the agent comes in, it will alkylate those, and that is called inter-strand cross-linking. Both of these are double strand cross-linking, right? Okay. So we said those agents attack or target the nucleophilic groups on nucleic acid bases. So what are some examples of those nucleophilic groups? Examples are like nitrogen number 1 and nitrogen number 3 of DNA, adenine, and also, as we said earlier, nitrogen number 7 or the amine nitrogen of cytosine. Those are some examples of the nucleophilic groups. Also, there is a possibility to attack the oxygen of guanine or the nitrogen of the amine, but those are less nucleophilic. Okay, the strongest one is the nitrogen number 7 of guanine. This is the strongest nucleophilic group among all of those. And we also said miscoding results from alkylation of nucleic acid bases, and that happens when with monoalkylation rather than with the double strand alkylation. The normal coding, as you know, in DNA, cytosine will code with guanine, and adenine code with thymine, right? That is the normal coding. This is the normal coding. But miscoding or abnormal coding happen with the alkylation. Why? As you can see here, like guanine will miscode with thymine instead of cytosine, because in the normal case, guanine like to be in the keto form. And I would like to remind you here about the keto-enol tautomerism. I think by now, and because you are on fourth stage, you know what do we mean by keto-enol tautomerism, okay? So in the normal case, guanine is in the keto form, but when the alkylating agent attached to guanine, guanine will prefer the enol tautomer, okay? And because of that, instead of forming code with cytosine, guanine will code with thymine, and that will cause miscoding. That will form unfunctional DNA. So either that DNA will not replicate or it will not transcript. And even if that DNA got transcripted, eventually the formed protein will be non-functional protein, and that will lead to apoptosis. Okay, as we said, normal base pairing to cytosine, guanine prefer the keto tautomer, while in the abnormal base pairing to thymine, the alkylated guanine prefers enol tautomer. All right. Let's start now talking about the alkylating agents and take some examples on that. The first one is the chlormethane, or it is also called michlorothiamine, either chlormethane or michlorothiamine. ethylamine. You see the structure here. It has electrophilic groups. Yeah, two electrophilic groups with a nitrogen and a metal. Very simple structure. Okay, it is the first nitrogen mustard used. It was used medicinally in 1942. It's an example of nitrogen mustard. Causes intrastrand and interstrand crossing. This agent causes both intra and interstrand cross-linking. It prevents replication, as we learned earlier. Monoalkylation of guanine also possible. So it's correct that it has two alkylating groups, but monoalkylation is still possible when one of them alkylate DNA and the other one got hydrolyzed by water. It is highly reactive because of those two lone pair of electrons, and because of that, because it is highly reactive, it cannot survive the oral route. We cannot give chlormethane or methylphenidine orally because it's going to react with water, it's going to react with protein, with blood, so we cannot give it orally. But analogs with better properties have been prepared. Those analogs basically have less reactivity. So the nitrogen in those analogs less reactive than the nitrogen in methylphenidine. Or that could be applied for the compound as a whole. We can say that those analogs are less reactive than chlormethane or methylphenidine. Up to you. So what's the mechanism of action? I think as a students of the College of Pharmacy, you like the mechanism of action. Or maybe you don't. Anyway, so first, the double bond of nitrogen will attack the carbon, and that will lead to the release of chlorine, as you can see here. This will form the aziridinium ion, which is highly reactive. All right. So in the presence of DNA inside the cancer cells, inside the nucleus, this is the N7 of guanine. So those lone pair of electrons on the nitrogen will attack that carbon atom, and that will open the bond to neutralize the charge on the nitrogen, and that will form the first alkylation, as you can see here. And because this process can be repeated again, so you can lose the other carbon to form the aziridinium ion again, and that will react with another guanine, or maybe cytosine or adenine. Okay, but mostly guanine, and mostly N7, the nitrogen at position 7 of guanine, because it is the strongest nucleophile. And that will cause either, if those two guanine molecules are on the same strand, that will cause intrastrand. If they are on different strands, it will cause interstrand crossing. We said that other analogs have been prepared with better properties. You can see here the structures of those analogs. First one, the structure number one, the R group here is phenyl instead of methyl in chlormethane. So the aromatic ring is electron withdrawn. Okay, if it is electron withdrawn, that will lower the nucleophilic strength of the nitrogen. Okay, that will lead to less reactive alkylating agent, and that will give us less side reaction and less toxicity or less toxic agent. Okay, the second one, which is melphalan, also the aromatic ring is present here. This is the aromatic ring, but and that will lead also to less reactive alkylating agent, just like structure number one. But milphenol mimics phenylalanine. As you can see here, this group is mimicking phenylalanine. So this agent will be transported into cells by transport protein, because as you know, the amino acid transported inside the cells by transport protein, because cells need those amino acids to form different proteins to make different enzymes. So the cells, and since the cancer cells more than the normal cell in their division, so they need to make more proteins and more enzymes. That's why this agent will be transported into cells by transport protein. Another example of using building blocks to increase the entry of the agent into the cell is the uracil mustard. In uracil mustard, they use uracil ring. This is the uracil ring, which is also an electron withdrawn, and that resulted in less reactive alkylating agent. Okay, that alkylating agent mimics the nucleic acid base, which is the uracil, and that's why it is concentrated more in fast growing cells than in normal cells. All right. Other analogs are estramastine. Is estramastine. In this agent, they use urethane group. This group here is called urethane. Why they use urethane? Because it's an electron withdrawing group, okay, that lower the nucleophilic strength of the nitrogen, just like the aromatic ring. So it's not only the aromatic ring that can lower the nitrogen, but it is the urethane also can do the same work. Also, this alkylating agent is attached to estradiol, which is a steroid. And as you know, steroids are lipophilic, and steroids can enter the cell freely. So this agent will be capable of crossing cell membrane because it has a steroid which is it is lipophilic, or we can call it hydrophobic. Okay? Lipophilic, hydrophobic, lipophobic, hydrophilic. Another agent is bendamustine. It's a more recently approved agent. As you can see, it applies the same principles as in the other agents that we discussed earlier. Okay. Other alkylating agent is the cyclophosphamide. You can see the structure here of the cyclophosphamide. The cyclophosphamide is the most commonly used alkylating agent. It's the most commonly used one. Out of all the alkylating agents, this is the most commonly used one. Why? Because it is non-toxic product that got converted inside the body to the alkylating agent. Okay, so because it is non-toxic and because it's a product which is non-reactive, it can be given oral. So it is orally active, not like the chlormethyl. Okay, the cyclophosphamide, as we said, it is converted inside the body to the active agent by the action of the cytochrome P450 enzyme inside the liver. The cytochrome P450 will oxidize this position of the cyclophosphamide. It will add the hydroxyl group. Then this will lead to the degradation, as you can see, and the opening of the ring. First ring opening, after ring opening, degradation of the molecule will happen, and that will form the cytotoxic alkylating agent and acrolein. The problem is that acrolein is associated with toxicity. That is the problem with cyclophosphamide. Toxicity is or can be reduced by administering sulfhydryl donors. Why sulfhydryl donors? Because they found that acrolein interact with proteins at the cysteine amino acid. So it will interact with the SH group of cysteine. So that is why the toxicity could be or can be reduced by co-administering sulfhydryl donors, such as N-acetylcysteine or mesna, which is sodium 2-mercaptoethane sulfonate. All right. The analog of the cyclophosphamide, just like the E-phosphamide or the I-phosphamide, it's related drug to cyclophosphamide, as you can see from the structure. It has similar mechanism of action, but it suffers the similar problem because it is going to form acrolein, and that acrolein will be toxic. Another example is ivophosphamide, which is structurally related to E-phosphamide. As you can see here, instead of chlorine, we have bromide and bromine atoms instead of chlorine, but it's a product, just like E-phosphamide and cyclophosphamide, but this one is a hypoxia activated product. So what do you mean by hypoxia activated product? That means this enzyme will be activated only in mediums that are deprived in oxygen, mediums that have low oxygen concentration. Okay? Right. So first, an enzyme catalyzed reduction of the nitro group will form the hydroxylamine group. Okay? Then this leads to the degradation of the molecule, as you can see here from the figure, that will form the alkylating agent. Right. If you have any question, you can add or submit your question through or as comments through the Google Classroom. Okay? All right. We talked about the nitrogen mustard. Now let's talk about the nitrosoureas. Example on the nitrosoureas are the lomustine and the carmustine. Nitroso because it has a nitroso group, this one, and urea is this part of the molecule. That's why they are called nitrosoureas. Okay? Those decompose in the body to form an alkylating agent and a carbomoylating agent. Okay? Well, and here is the mechanism for that decomposition. First, a hydroxyl group will abstract the hydrogen from the urea. That will lead to the degradation of the molecule, as you can see, to form the isocyanate and the alkylating agent. The isocyanate is considered as the carbomoylating agent, which will carbomylate protein, which will attack the lysine, will form this adduct, while the other part of the molecule will undergo degradation again. It will lose nitrogen gas and will form the hydroxyl group again, and that will form the alkylating agent, which will first alkylate DNA through this carbanion, this positive charge carbon, then will undergo the same cross-linking reaction that you saw earlier, which will kick the chloride ion out and form cross-linking. Okay. Here, this agent, the alkylating agent, will alkylate DNA and prevent transcription, and the carbomylating agent will carbomylate protein and prevent the repairing enzyme. Those proteins or repairing enzyme from repair the damage that happened to DNA. All right. These agents causes interstrand cross-linking, and they cross-link between either guanine or guanine cytosine, so they don't attack adenine. The carbomylating agent, as we say, react with lysine residues on a protein, and this may inactivate DNA repair enzyme because it's going to form covalent bond with the enzyme, and that is going to form inactive enzyme. Okay. Another example is the busulfan. This is the structure of busulfan. It is a synthetic agent. Okay. This one used as an anti-cancer. That's why we are talking about it here. It causes interstrand cross-linking, just like the other agents. You can see here the mechanism of action of busulfan. As we said, this one is the strongest nucleophile in DNA, the nitrogen at number 6. So those two lone pair of electrons will attack busulfan at this carbon, and that will open up the molecule. This will lead to the release of metal sulfate and a DNA adduct. But since this has two groups, the busulfan has two sulfate groups, so another nitrogen at number 7 will also react with the molecule and causes the interstrand cross-linking. Of course, this DNA is the same as this DNA. These are both the same DNA, not two different DNAs. The same DNA. Okay. Okay. Another example is the dicarbazine. You can see the structure here where the R group is methyl. It's a prodrug, just like the other one. It's activated by demethylation in liver. Okay. Decomposes then to form methyl diazonium ion, which alkylates guanine groups. And there's the scheme or the figure or the chemical reaction for the mechanism. So first, by the action of the cytochrome P450 enzyme in the liver, this will hydroxylate dicarbazine at this methyl group, the same as this R group. Okay. Then that will lead to the decomposition of the molecule and the release of formaldehyde. In the presence of photon, and as you might know, the cancer cells are acidic in nature. So in the presence of photon, this will form the methyl diazonium ion and the A1C. The A1C is just a natural byproduct for metabolism. So the A1C is not toxic, not like the acrolein, and the methyl diazonium ion will form nitrogen gas that will be released, and that will methylate DNA or alkylate or methylate guanine. Okay. Another example is the mitomycin C. This is a natural product, unlike the other ones which were synthetic compounds. This one is a natural product. Okay. It's a prodrug also activated in the body to form an alkylating agent. So if we say compare and contrast mitomycin C and let's say busulfan. Busulfan is synthetic agent, mitomycin C is natural product. Fossulfine is a prodrug, gentamicin is also a prodrug. Okay, that's how you compare and contrast. One of the most toxic anti-cancer drugs in clinical use due to its ability to alkylate DNA. It is one of the most toxic because of its ability to alkylate DNA. So, as we said, it's a prodrug. First, it is going to undergo reduction. Or these two carbonyl groups will be reduced to hydroxyl groups, as you can see in the figure. Then, after that, release of methanol from the molecule and decomposition and ring opening will form the alkylating agent. This alkylating agent will alkylate nitrogen on DNA. As you see here, it is the imine of guanine. So it's not, so as we said earlier, it's not only the nitrogen number 7 that could be alkylated. It could be another group. Okay? This will attack here that form the first adduct. Then, because DNA has more than one nucleophilic group, it will attack again, and that will form the cross-linking DNA. And as we said earlier, if both group on the same strand is going to form intrastrand, but in this figure, you can see it is forming interstrand because those groups are on different DNA. Different strands. This process will be associated with the release of carbon dioxide and ammonia. Okay. Other example is the CC1065, which is a natural product. It's a naturally occurring agent. As I said, it's a natural product. It binds to minor groove of DNA because, as you can see here, it has some planar rings. Okay, so those will be able to bind to the minor groove of DNA, and it alkylates adenine bases. Instead of guanine, we saw that those agents attack guanine. This one alkylates adenine more than guanine. And this one is 1,000 times more active than cisplatin in vitro. And we are going to talk about cisplatin in a minute. Adoxylicin is an analog of CC1065, but it's a simplified synthetic analog of CC1065. Okay, so again, what drug development strategy was used here is simplification, okay, rather than rigidification or substituent modification. This is simplification. And why we do simplification? Because it is easier to synthesize simple molecules than complex molecules. This one is undergoing testing to use in antibody drug conjugates. Okay, and in other lectures we will discuss the antibody drug conjugates. All right. As I said, if you have any question, you can submit your questions through the Google Classroom. Okay, cisplatin. Cisplatin is a platinum complex that has two ammonia group, two amine groups, ammonium group and two chlorine. Those ammonium serve as the ligands, and the chlorine serve as the leading groups. It's neutral inactive molecule. It is also acting as a prodrug. The platinum, as I said, covalently linked chlorosubstituents. These are the chlorosubstituents. And the ammonia molecule acts as a ligand. It is activated inside the cell or inside cells with low chloride ion concentration. Why low chloride ion? Because if there is low chloride ion in the medium, these two chloride ions tend to be lost. Okay? The chlorosubstituents are replaced with neutral water ligands that will produces positively charged species that then will react with DNA. Okay? As you can see here from this chemical equations. This is the cisplatin inside, as we said, inside cells with low chloride concentration. Those two chlorine atoms will be replaced with water. First, either one of them or both of them. Okay, and that then will react with DNA and form cross-linking. As I said earlier, this DNA is the same as this DNA. These are not two different DNA molecules. These are the same DNA molecules. Okay. Again, it binds to DNA in regions rich in guanine units, just like other agents. Its intra-strand links are formed rather than interstrand. So that means it attacks guanine on the same DNA strand. Causes localized unwinding of DNA double helix. And as I said earlier, you need to read the introduction to know why we need unwinding of DNA for replication or transcription. So that's how it inhibits transcription, because it stops unwinding. Okay. Cisplatin is not the only one. There are some cisplatin analogs, just like the carboplatin. As you can see from the structure here, it has less side effects than cisplatin and satraplatin, which is the first orally active analog. Also, we have the oxaliplatin. In the oxaliplatin, they added this ring, which increase lipophilicity of the molecule. That will increase, or will make the agent cross the cell membrane easier because it's more lipophilic. But the problem with lipophilic groups, just like these, that is not good for, it's not good for solubility. Okay, that's why they added the oxalate ring to counteract the effect of the diamino cyclohexane ring. Okay, so they added the oxalate ring to increase solubility because the oxalate has polar functional. Now, if you don't have any questions, we have reached the end of our lecture for this week, and we will see you next week.